Hello everyone. So now we will study about RLC circuits. But before going to that RLC circuits, like RLC circuits, there will be two storing element, right? L and C, inductor and a capacitor. So it will be a second order circuit. So before going to that, you need to have a basic idea of second order circuit. So first we will learn that. So tell me what is a second order circuit? There will be two effective elements. The order of the differential equation will be 2. Same like first order. In first order only one storing element and order of the differential equation was 1 and number of poles was 1. Here number of poles will be 2 because it is a second order system, right? Or second order circuit. And this point is just you need to remember, okay? The meaning of this point you will understand in signal systems and control systems, okay? In both of the courses you will understand this meaning. Just you need to remember that for a stable system, all the poles should lie in the left half of S plane. I told you about S plane, right? Sigma j omega. This is the S plane. So here only all the planes will lie if the system is stable, okay? In the left half of S plane, okay? No need to like derive or anything. And in the network analysis, all the circuit you study, all the circuits are stable. In the network analysis, all the circuit that you study, they will be stable only, and for them the poles will lie in the left half of S plane only, okay? So all the circuits will be stable, so you don't need to think if the system is stable or not. Just for a reference I put this line, okay? Now in second order circuit, what will be the equation? The equation will be something like this: S square plus BS plus A equals to 0, like something like this. So it will have two roots, right? One root S of P1 and second root S of P2. So based on these roots, the system can be of different types. Like the roots can be of different types. No, the first category I am taking is that both roots are complex and conjugate. So what do I mean by that? So on a S plane, I will draw the roots. So how am I thinking to draw the roots? Is that both are complex and conjugate. And I will draw it in the left half of S plane because I know all the electrical circuit will be stable. So here I will draw. Both are complex and conjugate. Like if there is a complex root, that has to be conjugate for sure, okay? Both are complex and conjugate. So I am taking that my poles are minus alpha plus minus j beta, or that means my first pole is minus alpha minus j beta and the second pole is minus alpha plus j beta, right? So this point is minus alpha because this is real axis and this is imaginary axis, right? And this is minus alpha and this point is plus beta and this point is minus beta. This is minus beta and this point is plus beta. So what this will denote? This will be sp2 and this will be sp1 because sp1 is minus alpha minus j beta, right? So here the poles are what? Complex conjugate, okay? So this kind of system results in underdamped system, okay? Underdamped system. This kind of system results in underdamped system. Why is it underdamped? We will see that, okay? Like why we call that underdamped, we will see that. So now I am considering that my both initial and final condition are 0. What do I mean by that? Let's just assume there is a system. I give an input, I will get an output, okay? This system is underdamped. I am saying that the system is underdamped. That means I will have an underdamped response. Now I am drawing that response. So for that response, I don't know what is the initial value, what is the initial value, what is the steady state value. I don't know these values. I will be having a response from an underdamped system. I will be giving an excitation and I will get an output. Now I don't know what is the initial value of the output. I don't know what is the final value of the output. So I am considering both values are 0. So how will the response look like in case of underdamped system? When you find the roots are coming like this. You got a transfer function, then you find the poles are coming like this. Now you know the initial and final value, you don't know the initial and final value, but you are considering that both of the values are 0. So how will the response look like? the response will look something like this. Okay, I can make it in a better way. Is it called underdamping? Underdamp, right? So what is the actual meaning of underdamped is that there will be some oscillations. Like damping is inversely proportional to oscillations. Damping is inversely proportional to oscillations. That means zero damping is equals to infinite oscillation. Infinite oscillations. Now, if this is underdamped, what is this system? This system is underdamped, so there will be some oscillations, but the oscillations will die out. So the response will go something like this. Now the output will be stable. Stable means it will go to 0 because we are considering that our final value is 0. So now that output will be at 0 forever. Okay. So this is the steady state. So what do you mean by underdamped? In underdamped response, the damping is not enough. In underdamped response, damping is not enough to kill the oscillations. The oscillations. But eventually, eventually, what is the spelling of eventually? Eventually, the oscillations will die out. Okay, we are not checking any condition. We just understood two things here. You find the poles. The poles are coming like minus alpha plus j beta minus alpha minus j beta. If the poles are coming something like this, the response will be something like this. Okay. If there are two complex conjugate poles, that means the system is underdamped. Underdamped means there will be some oscillations, but finally the oscillations will die out. Now there is an example. From this you will understand more. So there is a motor. You want to run that motor at 1000 rpm. Okay. So there is a motor. There is a system of a motor. You give an excitation that run it at 1000 rpm. So how should the response look like if the system is underdamped? Okay, the system is underdamped. So how should the response look like? So what is the condition? There is this underdamped system. You are giving an excitation. What is the excitation? Excitation is run at 100,000 rpm. The system is underdamped. So since the system is underdamped, so what will be the final output? Final steady state output. What will be the final steady state output? That will be 1000 rpm only, right? Because you want your final output to be 1000 rpm. So since the system is underdamped, the response will oscillate around 1000 rpm and will reach steady state after some time, right? After some time. So how will the response look like? Okay, considering initial speed of motor to be 0. Considering initial speed of motor to be 0. Initial speed of motor to be 0, that means That means V naught 0 plus is 0, not V naught 0 plus. Okay, this is output, so I should write Y naught. Okay, not V naught, I will write Y naught. Y naught 0 plus is 0. From 0 to it is going to 1000. So how it will go? From 0 to it will go to 1000 because final output has to be 1000 only. So from 0 to it will go to 1000. So I'm just making my steady state value, that is this 1000. Okay. So it will go like this. It will have the oscillations around it, right? And then it will be stable. Okay, this is Y naught T graph versus T. This is what 1000 RPM. Okay, so what will happen? Look, there is a system, you give an excitation that run at 1000 RPM. You are collecting your output. So what will happen? From 0 it will start, 0 to increasing. Sometimes it can go to 1200, then it can come down to 800, then it can again go to 1100, then it can come down, then it can again go to 1050, then it can come down to 850, then it can go to 1020, then it will be stabilized at 1000. Are you getting my point? I am just saying that it can be 1200, it can be 1100, it can be 1050, it can be 1020. Similarly, it can be it can be 800, it can be 900, it can be 850, 950, then finally it will go to 1000 RPM. So if you are collecting your output, you will see that 1200, 950, like it is oscillating like this, but at steady state, after some time, there will be this constant 1000 RPM. Are you getting my point? This is what we mean by underdamped response, and this will happen when your transfer function has two complex conjugate root. This is the important thing that you need to remember. The response you will remember, but when this response will come, when your transfer function has two complex conjugate poles. Now coming to the second condition, and this is known as underdamped response. Okay. Now coming to the second condition where both of the roots are real but same roots. Here the roots are real but the roots are same. So how will the graph look like of sigma j omega? S plane it is. Real and same. So first I am making like this, the other one I will have to use some other pen. So there are these two roots. Okay, minus alpha. I will write two roots. SP1 is minus alpha, SP2 is also minus alpha. Same root is there. Okay. So now how will the response look like? That is the condition. Okay, how will the response look like? So I am considering my, and what is this system called? Like previously it was called underdamped response. This system is known as critically damped. Critically damped. That means there is enough damping to kill the oscillation. This is critically damped. So how will the response look like? Initial and final value 0. You will start from 0, you will go to 0. But how it will look like? It will just increase and then stabilize at 0. I will have to make a better graph. Okay. Yeah. So this is how the response look like. It will just increase and then stabilize to 0. Okay. Initial and final value at 0. So just it will stabilize to the final value. There is no oscillations. No oscillations. So what is the important point? In critically damped system, there are no oscillations and the response is faster. Okay. Okay. So we will take the same example. Now you are giving an excitation to run the motor at 1000 RPM. right? The same example, run at 1000 rpm, your final output would be 1000 rpm. Okay, you are saying that your excitation is, you are telling your motor to run at 1000 rpm and your final steady state output is 1000 rpm, right? Now you are giving that excitation to the motor. So how should the response look like? So initially it will start from 0, initial speed of motor 0 rpm. So it will start from 0 and finally it will go to 1000. So it will quickly go to 1000, right? It will quickly go to 1000 without any oscillation. No oscillations. There are no oscillations. Faster response, and this is 1000 rpm. So from 0 to 1000, this is not exponential. Okay, not exponential. This response is something like this. Faster response. Okay. Now two conditions we have covered. Complex conjugate poles, real pole, and both pole are equal. Now the condition is real pole but both are different. Okay. Look, this condition will never come, that minus alpha 1 plus j beta 1 minus alpha 2 plus j beta 2 or minus j beta 2. This condition will never come. If there are complex pole, they will have to be conjugate. If there are complex pole, they will have to be conjugate. Okay, I guess I should write it down, or this is basic mathematics, that if you solve a second order equation, right? If you solve any second order equation, if there are complex pole, they have to be conjugate, right? Because what is the solution of a second order equation? This is this minus b plus minus root b square minus 4ac by 2a. Let's just assume this is a negative value. So what you will have? Something negative. Let's just call it beta, j beta by 2a. So both of them has to be complex conjugate. So that condition will never come. Okay. So don't wait for that condition. Okay. This is the third response. Both roots are real but different. So two different roots can be there for sure. Right. Let's just call this one as alpha 1. Am I denoting it negative? Yeah, I'm not denoting it negative. So let's just call it minus alpha 1. Let's just call it minus alpha 2. So this I will call sp2, this I will call sp1. So your first pole is minus alpha 1 and your second pole is, two different poles are there. Okay. So what do we call that? Overdamped system. Overdamped system. Okay. So how will the response look like in overdamped system? It will be the same as critically damped system. Okay. Overdamped system means there will be no oscillations at all. Like damping is very high damping. Very high damping. That means there is no chance of oscillations. Here also there is no chance of oscillation. Here also, because this is critically damped, just damped, that there is no oscillations. But like this is the threshold. If you're like before this, there will be some oscillations. This is the threshold where there will be no oscillations. So designing this system is a bit tough. What I am saying is that designing this kind of system is very tough, because this is the threshold. Here only there will be no oscillations. This is the first condition when there will be no oscillations. Right? This is the first condition. And then after that, if you increase more damping, that means there will be certainly no oscillations. But what will happen? That is, the response will become slower. So in underdamped, you are having some response like this. sorry, in critical damped. In critical damped, you are having some response like this, but here you will have response like this. Okay, I will have to make it a look better. Yeah. Yeah. So this is the steady state value. Okay, from 0 to 0 it is going. Slower response. What you are having? You are having a slower response. Okay. So this is a slower response. Good. Here there are absolutely no oscillations, but the response is slower. Now the same example, what we are saying, we are asking the motor to run at 1000 rpm. Our final output will be 1000 rpm. Final steady state output will be 1000 rpm. Okay, so how will the response look like? Minus t, this is 1000 rpm. The response will be slower, right? As slower response. So what will happen? You will give a 1000 rpm excitation. From initial speed of motor is 0. Initial speed is 0 rpm. So from 0 to it will increase 0, 100, 200, 300, 400. Slowly it will increase. In this case, what will happen? In critically damped system, from 0 to 500, 1000, bus steady state very quickly. In this case, what will happen? 0 slowly increase, then 1200, then 950, then like this oscillation, and then 1000. So if you see, everyone wants to design this system, right? It has to be critically damped because faster response and no oscillations. But this is very tough to design. You can't really design. Okay, but now you will say, I will design this system. I will design this system. But and overdamped, because in overdamped system there is no oscillations, so it is also good. But the response is slowest. In case of overdamped versus underdamped, in underdamped there are oscillations, but the response is faster than the overdamped. So we will note it down. Okay. So here I can add a page before this. Speed of response. Speed of response. So which is the fastest? Which is the fastest? Critical damped, then underdamped, and then overdamped. Okay, this is the fastest. Okay, now which system you need to design? Sometimes in some system you don't need any oscillations, like you don't want your final output to go 1200 rpm. Okay, or anything can be there. It can be speed, it can be anything, right? So you don't want any overshoot or undershoot. What do I mean by overshoot and undershoot? Like this was the response for underdamped. So this is known as overshoot. Like 1000 you wanted to go and you go to 1200. So 200 is rpm is your overshoot here, and this is your undershoot. You wanted to go to 1000, but you are going to 900. So this is your undershoot, that is 100 rpm. or minus 100 RPM, you can say. So you don't want some undershoot or overshoot in some systems, and some system it is fine to have this, but in some system you need faster response, so you will prefer underdamped. And in some system you need slower response but you don't want any oscillations, so then you will prefer overdamped. Okay, this is fastest and no oscillations, but this is very tough to design. No oscillations, but it is very tough to design. This is underdamped, not the fastest but not the slowest. Okay, so how should I write it? Not the fastest, faster than overdamped. I can write faster than overdamped. Faster than overdamped. No oscillation. No, sorry. Oscillations are there. Oscillations are there. Okay, and not very tough to design. You can design it. This is the slowest, but no oscillations. So depending on the requirement of the design, depending on the requirement of the system, you design your system. Okay, it will be overdamped or underdamped. Based on that you will design. Okay, so if you keep damping factor high, that means it is your overdamped. What is damping factor, that we will understand. Okay, what is damping factor, that we will understand. If you are keeping damping factor high, that means it will be overdamped. If you are keeping damping factor low, that will be underdamped. So now we will take the example of RLC circuits, but before that we will understand one more condition, that is both roots are completely imaginary and they are conjugate as well, because if they are imaginary they have to be conjugate. Okay, this is sigma, this is j omega. So the roots are by minus beta, it is beta, this is minus beta. Okay, so my sp1 is minus j beta and my sp2 is j beta. Like this is my sp2 and this is my sp1. So this we call undamped. Okay, no damping, there is no damping at all. That means there are infinite oscillations. That means the output will keep on oscillating. The output will keep on oscillating. So we can only consider the final value, sorry, initial value. We can't really tell what will be the final value here because the output will keep on oscillating. There can be some DC value, some DC, like what is the DC value of a sinusoid? What is the DC value of a sinusoid? This sinusoid. DC value of this sinusoid is 0, and there can be some maximum value that it cannot go above this much of, it cannot go above this much of final, this much of value. Like the maximum value a sinusoid can have is a sin omega t. What is the maximum value a sinusoid can have? That is a, right? So it will have constant oscillations. So how should the response look like? So it will always oscillate, but it will oscillate around one maximum value, that is for sure. This maximum value is constant, so this is always oscillating, always oscillating. But in RLC circuit we will not study this, because in RLC circuit there will be this resistor, right? This resistor will be there, that will not happen, that will not let this happen, because resistor dissipates energy. But if there is no resistor involved, only LC circuit is there, there is no resistor, so there can be constant oscillations, right? So this will be studied in LC circuits or LC oscillator, we can say LC oscillator. Now we are going to study about RLC. then we will study about LC oscillator. So let's move on to our topic, that is RLC circuits. Okay, so now first we will be studying source free RLC circuit. That means there is no source involved. There are initial conditions. Inductor is having initial current of I naught, the capacitor is having initial voltage of V naught. So like let's write the equation for I. Okay, you can write the equation for VCT as well, VLT as well, VRT as well, ILT, IRT, any component, any expression you can write, right? Any voltage or any quantity you can write. Understood? So let's write the expression for current. The expression for current. Okay, we are writing it for current. So what we are doing, apply KVL. So applying KVL, IR plus, this is having initial current, but you are writing the voltage. So if you are writing the voltage, there is no meaning of initial current. Like what I am saying, this is an inductor which is having initial current of I naught, and the current is flowing through it is I. Initial current of I naught is there, and you need to write down the V voltage. What will be the voltage V? That will be L di by dt. The initial current will not come in action in case of writing the voltage, right? Because this is a constant current. If you differentiate it here, the like let's assume it is having two component I1 and 0. Sorry, I naught. I1 plus I naught. Like this is the final current I, and it is initially having I naught current. So L di by dt plus what is the differentiation of this? That will be 0. So eventually this will come. So I was writing the KVL. So IR plus L di by dt, IT I should write in time domain. It is like this is the current that is flowing. So drop will be like this. In the inductor it is flowing like this, so drop will be like this, and here in capacitor it will be like this. So if you are starting from here, plus, plus and plus, all will have the same sign. So what I can write, IR plus L di by dt, IT into R plus, since we are writing the potential, so you will write initial potential as well, V naught plus 1 by C integration IT dot dt is equals to 0. Okay. Yeah. So why did I write the initial potential? Because what is VC? VC is initial voltage plus 1 by C integration I dot dt. Right? So this is what I have written. So now since there is an integration term, I will differentiate on both of the side. So what I will get, R dit by dt plus L d square it by dt plus it by C is equals to 0. D square it by dt plus R by L dit by dt plus 1 by RC it is equals to 0. So how we can solve it? D square plus R by L d plus 1 by RC into it is equals to 0. This is what? F of d. So you will be finding the roots of this, right? D square plus R by L d plus 1 by RC is equals to 0. So d would be minus b plus minus root b square minus 4ac upon 2a. So how I can write it? Look, I will take this 2 here, right? I need to divide 2 everywhere. So can I write it like this? Minus R by 2L plus minus R by 2L whole square minus 1 by RC. LC. That's what I was thinking. It would be LC. LC, 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 LC. Root LC square. What did I do? If you are putting this 2 inside, it will be 4, right? 1 by 2 root x something. So you will write root x by 4. This is what is happening here, right? So it is going inside with being 4, and 4 is 2 square. So this is what I have written. This is simple mathematics. You can think about it. That's how I can write. So I can write it in this form: minus alpha plus minus alpha square omega naught square. So now based on alpha and omega, you will have different roots. So here your alpha is r by 2l and your omega naught is 1 by root LC. Right? So this equation will be valid for everything, not just for current. For like the complete circuit, this complete circuit is following the second order differential equation. Now if you write for current, if you write for voltage, if you write for voltage across inductor, capacitor, everything, everywhere you will get these two roots only. These roots only: minus alpha plus minus alpha square minus omega square. Okay, so this is what you will get. So basically there are two roots: minus alpha plus minus plus. Basically two roots are there. SP1 is minus alpha plus alpha square minus omega square and SP2 is minus alpha minus alpha square minus omega square. Okay, and alpha value is r by 12. You have to remember this. Okay, you have to remember this. For a series RLC circuit, alpha is r by 12 and omega naught is 1 by root LC. For a series RLC circuit, the roots are minus alpha plus minus root alpha square minus omega square, where alpha is r by 2l. Because in parallel RLC it will be changed. So alpha will be changed, omega naught will remain the same for parallel RLC as well. So for a series RLC, alpha is r by 2l. Okay. Now I am asking, you need an underdamped response. For underdamped response, what is the condition? What is the condition? Poles must be complex and conjugate. Complex conjugate. That means alpha should be less than omega naught, right? Alpha should be less than omega naught. That means this part would be imaginary, right? So roots will be what? What are the roots? Minus alpha plus minus alpha square minus omega naught. Now this part is less than 0. So what I can do? I can write it something like this. Are you getting my point? What did I do? Let's just assume this is what I am having. So what I will do? This I can write, no? Right? So this is what I have done. Right? Since omega naught is greater than alpha. So I am calling it like alpha plus minus j omega d. Now if you remember, for a differential equation, your roots are minus alpha minus j omega d and minus alpha plus j omega d. Now go to the differential equation class notes. I told you, if the roots, we just described the condition for different kind of roots, alpha 1, alpha 2, right? For alpha, like roots are alpha and alpha, and one condition was this: alpha 1, no, sorry, alpha is the same, and this was the condition. For these roots we defined, for these roots we defined, for these roots as well we defined. So what was the solution? Then the solution of differential equation yt, that would be e to the power minus alpha t. The real part will go to exponential and the complex conjugate part will go to sinusoid and cosinusoid. So this is the response. So for a underdamped response, alpha should be less than omega naught. What is alpha? R by 2L should be less than 1 by root LC, right? This is the first thing. What is the second thing? What is the output? Output would be what? E to the power minus alpha t C1 cos omega dt plus C2 sin omega dt. If you just plot it, the response will look something like this only. How will the response look like? Like this. Like this. So this is the final response. Now, now for IT, what will be the IT? IT would be e to the power minus alpha t C1 cos omega dt plus C2 sin omega dt, right? In the given circuit, what is the value of I of 0 plus? In the given circuit, what is the value of I of 0 plus? I of 0 plus is I naught. So if you put in this equation, if you put I of 0 plus, what you will get? This will be 1, this will be C1, like cos 0 is 1, cos 0 is 1, sin 0 is 0, so only C1. That means C1 is equals to I naught. So similarly, by other conditions, you can find the value of C2 as well. Find the value of C2 as well. What is the value of I of infinity? This is the first thing. What is the value of I of infinity? I of infinity. If you put infinity here, it will go to 0, right? And this is the equation second. So your graph will start from I naught and it will go to 0 with constant oscillations. So if you want to draw the graph of IT, it will start from I naught and will go down to 0. Like why it will be 0, by the way, I of infinity, why it will be 0? Because at infinity, this capacitor will be open circuited, right? And the inductor will be shorted. Since it is open circuited, there can be no current flow, right? For this, I can make the circuit as well. This is circuit at t equals to infinity. That means a steady state. So it will start from some value I naught and will go down to 0 with some constant oscillations. Now we don't really know the oscillation will be negative or not, or it will be always positive. So you can't really comment on that. But one thing that you know, there will be some oscillations and then it will go down to 0. Okay. So I will make the graph like this. So this is how the current waveform will look like. It will start from I naught. Now one more thing, since all the expressions will follow second order equation only. So if you want to write the expression of voltage across the capacitor, voltage across the capacitor, this is what I want to write. So what will be my VCT? What will be my VCT? My VCT would be e to the power minus alpha t C1 cos omega dt plus C2 cos omega d sin omega dt. But the thing there, that would be the C1 and C2 will be different. So what is the value of at t equals to 0? At t equals to 0, Vc0 at t equals to 0 plus Vc0 plus is V naught. That means C1 is equals to V naught. You can find C2 as well in the similar way. We will find when we solve numerical example. If I start finding here, it will be very difficult, right? You can find C2 in similar way, right? Now what will be your Vc at infinity? That will be 0. So how will the graph look like? It will be the same like this only. Okay, instead that I can copy it as well. C1 C2 will be different. Of course, here C1 was I naught, and in this graph here in this graph C1 is V naught, right? We are drawing the graph for VCT. So all the parameters will follow this kind of equation. VLT as well, e to the power minus alpha t C1 cos omega dt plus C2 cos omega dt. So what will be for VLT? You can also write that, right? For for VRT also you can write that. So shall we write for VLT as well? Okay, one more page. Now what will be your VLT? Now your VLT, that would be e to the power minus alpha t, same equation, but C1 C2 will be different, cos omega dt plus C2 sin omega dt. At t equals to 0, what is the value of VLT? Tell me. At t equals to 0 plus, VL0 plus is what? At t equals to 0, VL0 plus, that is at t equals to 0, we need to see. Okay, at t equals to 0, what is happening? This is a resistance R with the inductor is initially having the current I naught, and there is this capacitor which is having initial voltage of V naught, right? Initial voltage of V naught, and this is R. This is I naught R, and this I will call VL0 plus. So VL0 plus is basically my minus I naught R minus V naught, minus I naught R minus V naught. So at t equals to 0, what you are having here? C1 is equals to minus I naught R minus V naught. Similarly, you can find V2 as well. Similarly, you can find C2. Okay, and the graph will and this will be the graph, like it will start from here and that will be the graph. From negative value it will start and will go down to 0. Okay, so I guess I can draw the graph for VLT as well. Let's just assume this is the value. It will start from this negative value. And will go down to 0 like this. Okay, this negative value is. So when you solve the numerical example, you will get to know how to find the value. You don't need to mug up these values. The C1 value will be this or that. Okay, in numerical example we will find that. Okay, so this is how this is about the first condition, that was underdamped response, underdamped system. Now case 2, we need critical damped. So for critical damped, what do we need? Both roots should be equal, right? So what are the roots? What will be the roots? Roots are minus alpha plus minus alpha square minus omega naught square. If this value is 0, alpha is equals to omega. So for critically damped, roots are minus alpha and minus alpha, right? In the previous analysis, here our roots was minus alpha plus minus j omega d, where omega d was root omega naught square minus alpha square. You don't need to mug it up, you will remember it eventually, right? So your roots are this. The solution of differential equation. What will be the solution of differential equation? You tell me. Solution of differential equation. Tell me what will be the solution of differential equation. If two roots are equal, what is the solution? C1 plus C2t e to the power minus alpha t. In basics of differential equation, I have told you everything. I have taught you everything, right? This has been taught. What will be the solution? Because at that time I told you it will be used later on. So here it is being used, right? So C12 plus C2t minus alpha t. Okay. So and similarly, the response here was like something like this. Now so basically for underdamped response, for critical damped response, damped response. This is the case of series RLC. Don't forget. Okay. Because in parallel RLC, alpha will change. So alpha is equals to omega naught. What is the value of alpha in series RLC? That is R by 2L. How will you remember actually? So in series RLC, alpha is R by 2L. Okay. And in parallel RLC, we will solve it. It will be 1 by 2 RC. Okay. So series L, SL, Sri Lanka. Okay, that's how I remember it actually. Okay, series and L. In series, L will come. Sri Lanka. The word name Sri Lanka, SL, you can remember. And in parallel, C will come. PC, personal computer, or Piyush Chawla also. Okay, so in parallel, C will come. In parallel, C can come, and in series, L will come. Okay, so SL and PC. And how will you find the value? How will you remember the value? What is the time constant for inductor case? That is L by R. Just reciprocal it and divide by 2. What is the time constant for RC? That is RC. Just reciprocal it and divide by 2. That's how I remember it actually. Parallel capacitor. What is the time constant in case of capacitor? That is RC. Reciprocal and divide by 2. That's it. Okay. So that's how I remember it actually. So alpha value will be 1 by 2 RC in case of parallel, that we will see. Okay. So R by 2L is equals to 1 by root LC. Okay. This is the condition. Okay. So the response. So solution of differential equation, basically this is Yt. The response is Yt. Now let's find for It, for current It. So what will be the expression of It? It will be C1 plus C2t e to the power minus alpha t at t equals to 0 plus It is I naught. And if you put t equals to 0 here, what you will get? Equals to C1. Are you getting my point? At t equals to 0, if you put t equals to 0 here, this will be 1, this will be 0, so only C1. So C1 value is equals to I naught. Okay. Similarly, you can find C2. And what will be your I infinity? I infinity will be 0 only, right? Because capacitor will be open circuited, so it will be 0 only. So the graph will start from I naught and will go to 0. But remember one thing, there will be no oscillations. So how will the graph look like? It will start from I naught and it will go to 0. Now the thing is that, will there be current ever more than I naught? Like initial current is I naught, but the current will be more than I naught or not? I don't think the current will be more than I naught. I naught is the maximum current only. The initial current is I naught. We can't have more than I naught current because there is the resistor involved. So it will quickly go down to 0. Right? It may not be exponential response. Okay. Like it depends on the value of C2. If you are getting C2 equals to 0, let's just assume you solve the equation and you get C2 equals to 0. So the response will be exponential. If C2 is not equals to 0, the response can be something different. Yaar. Okay, let me pause it and then make it. Okay, so that's how IT graph will look like. Similarly, what will be VCT? VCT will be something like this only. C1 plus C2t e to the power minus alpha t. At t equals to 0, what is the value of VCT? So VC0 plus is, at t equals to 0, you will get C1, that is equals to V naught. So the graph will look something like that only. And at t equals to infinity, what is the value of VC infinity? At infinity, the capacitor will be open circuited and there will be no current, so it will be 0 as well. So the graph will look something like this only. Okay. Okay, so no need to make the graph. So this is for VCT. This was for IT. For VLT as well you can write. For VRT as well you can write. Right? Let's just write it for VRT. For VRT if I am writing. So what will be your VRT? VRT would be C1 plus C2t e to the power minus alpha t. Now all this will be decided on the value of R, L and C. The way value of R, L and C is selected, it will be critically damped or underdamped or overdamped. Right? So we don't know the value of RLC. When we solve the numerical example, we will get to know. Okay. But in the exam, most probably they will not ask you the expression. And if they ask you the expression, there will be 4 options. So you will not need to do the high calculations actually in the exam. But here we will do the calculation. But in exam, you can solve the question smartly with the options, right? Or they will ask you the waveform. So the waveform will be something like this only. And if they are asking the waveform, you will have 4 options. So only one waveform will be like that. So you don't need to do any calculation. You just need to know that in underdamped there will be oscillations. In critically damped there will be no oscillation and the response will be faster. And in overdamped the response will be slower with no oscillations. So that you will understand by looking at the options. So what about VRT? This is VRT at t equals to 0, VR 0 plus. What is the value of VR 0 plus? VR 0 plus, that is minus I naught R, right? Right, minus I naught R, because this current is flowing like this. I am calling this as VR. Okay, it depends what I am calling VR actually. So what is your VR, that depends actually. So I am calling what I am calling as VR, that is the important thing. Okay, so this is inductor, like that will be given to you, what is VR, what is this. So I am calling this as VR. Okay, this is the resistance R. So initial current here is I naught, right? So I naught current is flowing here. So VR 0 plus is minus I naught R. What will be the value of VR at infinity? That will be 0 only, right? So from minus I naught R it will start and will go to 0, right? So what will be the graph for VRT? So in the similar way you can make these graphs. From minus I naught R it will start and will go to, quickly it will go to 0. The response will be exponential or something different, that depends on the value of C2. Right? How we will find the value of these things, that we will see. Okay. Let's move on to the next problem. So here, not the next problem, this is the next condition. Here it is overdamped. So overdamped, both roots will be different. So what are the roots? Minus alpha plus minus alpha naught square omega naught square. Okay. So roots will be different. So my SP1 would be minus alpha plus alpha square minus omega naught square, and my SP2 would be minus alpha minus omega naught square, alpha square minus omega naught square. So these will be two real value and different will be real, right? Real and different value. So since this is a longer expression, I am calling this one as alpha 1 and this one as alpha 2. Okay, this one as alpha 1, this one as alpha 2. Okay, but these values will be negative. Are you getting my point? Alpha 1 will be negative. This will be negative and this will also be negative. Why is it negative? When we draw the graph, what did we say? This is the first root, this is the second root. This is what I said, right? This is the graph for both roots real but different. So what I am doing here, minus alpha 1, this is minus alpha 2. Yeah. So negative roots are there, no? So the same thing is this, right? The values will be negative. So I can make a graph as well. This is sigma and this is j omega. One will be lambda 1, one will be lambda 2. Which will be lambda 1, which will be lambda 2? Tell me. This will be lambda 2, this will be lambda 1. Why so? Because this is less negative. Let's just assume this value is 4, this value alpha is 5. So minus 5 plus 4, it will be minus 1. And minus 5 minus 4, that will be minus 9. So alpha 2 will be, lambda 2 will be more negative. So that's why this is lambda 1 and this is lambda 2. Okay, and this is a negative value. Okay, so what will be the output? The output, and how can write solution of the differential equation? Solution of differential. This you must remember, right? Even if you have forgot the previous two, but this solution you must have remembered. Two different roots. So what will be the solution of differential equation? That will be c1 e to the power lambda 1t plus c2 e to the power lambda 2t. This is your yt, right? So for overdamped response, alpha is greater than omega naught. What is alpha? Alpha is r by 2l, that is greater than 1 by root lc. In case of series RLC, this is going for series RLC. So what I am doing, I am writing for IT, right? So IT would be C1 e to the power alpha 1t plus C2 e to the power alpha 2t. What is the value at t equals to 0? Here it will be C1 plus C2 and that is equals to I naught, right? The value at t equals to 0 because capacitor will be shorted and I naught current will be flowing. So that value is I naught. What is the value at t equals to infinity? Will it be infinity or 0? We know that it will be 0 from circuit analysis because the capacitor will be open circuited and inductor will be shorted. The capacitor will be open circuited at t equals to infinity and inductor will be shorted. So the current is going to be 0. But if you put infinity here, someone will say that e to the power infinity it will come. So it will be infinity plus c2 into infinity. Is that right? No, it's wrong because alpha 1 and alpha 2 are negative. In reality, alpha 1 is minus 4 something like this and alpha 2 is minus 9 something like this. So these values are negative actually. Okay, these values are negative actually. If you put t equals to infinity, it will go to 0. Here if you put it t equals to infinity, it will go to 0. Are you getting my point? So I of infinity will be 0 only. So from I naught it will start and will go to 0. But slowly. The response will be slow. The graph of IT will be something like this. From I naught it will start. It will go to 0 but slowly. Okay. Similarly for VCT and VLT. Similarly for all other expression. Right? You can do this for all other expression. A slower response. I'm saying a slower response. Right? I hope you have understood. Right? So let's just see a solution. Let's just see a question. So this is what they are saying. This is a series RLC circuit. You need to find the value of capacitor C to have a critically damped response. So what is the thing for critically damped? For critically damped, like you don't need to remember much of the things. I will just revise. I will just revisit the concepts. Okay, after solving this problem. For critically damped, alpha is equals to omega naught. What is the value of alpha? That is r by 2l. What is the value of omega naught? That is 1 by root LC. So just put the value that is given. R is 40, 2l will be 8, 1 by root L value is 4, and C you need to find 5. 25, C would be, this would be 5, so it would be 5, it would be 25 into 100, so it would be 1 by 100, 1 by 100 we will get, I guess. So 5 by 25 by 4C, C would be 1 by 100, so basically it will be 10 millifarad, right? So the capacitor will be 10 millifarad. Am I right or wrong? 10 millifarad, 10 to the power minus 2. 10 to the power minus 2, right? If it is 10 to the power minus 2, it will become 10 to the power minus 1. 10 by 2 it will become. Yeah, it is fine. C value is 10 millifarad. Okay. So this is a simple problem. So what we have studied in this complete analysis, first we studied about the responses. Critically damped response, under damped response, critically damped response, over damped response. For under damped response, there are oscillations and it will stable down to a final value. For critically damped, faster response, no oscillation. For over damped, no oscillations but a slower response. Okay. Then we saw the analysis of series RLC. So in series RLC, we solve the equation. We go to know this is our roots, minus alpha plus minus root alpha square minus omega naught square. Okay, this is our root that you need to remember. This thing you need to remember, and you need to remember the value of alpha and omega naught as well. That's for series RLC. That is r by 2l and omega naught is 1 by root LC. Okay, so this thing you need to remember. Okay, only this thing you need to remember, nothing else. Right? Then you will have the values, right, of alpha and omega naught. So then you can find the nature of the roots. Based on the value of alpha and omega, you will find the nature of the roots. Let's just assume our alpha is less than omega naught. So our nature of roots will be something like this. That means we will have a complex poles, right? We will have complex pole. We will have complex pole and both will be conjugate. So our response will be underdamped, because in case of underdamped response, the poles are conjugate, complex conjugate. This thing also you need to remember. In case of underdamped response, the poles are complex conjugate. So the response will be something like this: e to the power minus alpha t c1 omega dt plus c2 sin omega dt. Omega d is root omega naught square minus alpha naught square. You don't need to mug it up. You don't need to mug up this thing, because you will find the response eventually. This will be a value, this will also be a value. So from that you will be able to write the response. This response also you don't need to mug up. You just need to remember that if I am having a complex response, how should my differential equation look like? So what should be the response of my differential equation? So this will be the response of my differential equation. From there you will find the values of constant C1 and C2. Then you will find the values of constant and you will put in the value. Then you can draw the graph. And if they are asking just the graph, you just need to know the initial and final value. Initial value is I naught, final value is 0. So just you can make the graph with the oscillations. So this is how the graph will look like, right? If just they are asking just the graph. So if they are asking just the graph, then you know initial and final value, and you know how the response in between will look like for a underdamped response. Similarly, for a critically damped, what should be the roots? Roots should be equal. So alpha should be equals to omega naught. So this is for critically damped. Then you can write down. Then you can see all these graphs. The graphs will be having no oscillations and will quickly stable down to the final value. Then similarly for overdamped, the graph will have no oscillation, but it will slowly, it will go slowly, right? It will settle down to the final value slowly. And the nature of roots will be two roots, but different, and both should be real. So that's it. Okay, these three kind of response you can have in case of series RLC. In parallel RLC as well, these three kind of response you will have. Just the value of alpha will change, everything else will remain the same. Then we saw this example this is a serial RLC. You need for critical damped alpha should be equals to omega naught. So from there you go to the value of capacitor C. Okay, now we will see parallel RLC. Okay, so let's see the concept of parallel RLC circuits. So here as well, source free it is. There is no source. Okay, no source involved. So here as well, the same condition, inductor is having initial current of I naught and the capacitor is having initial voltage of V naught. So here we will apply KVL. Why we are applying KVL? KCL, sorry, KCL. Because like here the voltage across all of them is the same. So like in this branch current, in this branch current, and in this branch current, I can write that current. So it will be more easier for me to write, right? But like how can I write KCL here? Sorry, how can I write KVL here? I can't write KVL here. Why so? Because voltage across all of them is same. And in the previous analysis, the current across all of the component were same. So I can't write KCL there. Like I can't write current equation there. So I have to write voltage equation. Now the voltage across all of them is same. So I can't write voltage equation there. I have to write current equation. So applying KCL. Are you getting my point? Why I am applying KCL? Because here current across all of the component is different. So what is the current in capacitor? That is C dVc by dt. Initial voltage doesn't matter, right? While writing the current, initial voltage doesn't matter. C dVc by dt. What is the current in this branch? In the inductor branch, that is I naught plus 1 by L integration Vc dt. From minus infinity to t you can write like minus infinity to t you can write if the switch was closed at t equals to 0, you could have written from 0 to t. Okay, why Vc? Because across all of the component you are having one voltage, that is Vc. So 1 by L integration minus infinity to t Vc into dt. And what is the current in this branch? That is Vc by R. So this is the equation. Now I have to differentiate both of the side. Differentiate. Just I will write differentiate. What I will get? C dVc square by dt plus I naught, differentiation I naught will go to 0, and now it will be Vct by L plus this will be 1 by R dVct by dt, right? So d square Vct by dt plus 1 by Rc dVct by dt plus Vct by Lc is equals to 0. D square plus 1 by RCd plus 1 by Lc Vct is equals to 0. So what will be the roots of the equation? F of d will be put equals to 0. Okay, you can find the roots, right? The value of d will become minus 1 by 2 Rc plus minus root 1 by 2 Rc whole square. You can solve it, right? I just remember it, that's why I am writing it. Okay, you can solve it on your own. So basically roots are what? Minus alpha plus minus alpha square minus omega naught square. So alpha is 1 by 2 Rc and omega naught is 1 by root Lc. So just the alpha has changed. Nothing is changed, only alpha is changed. Okay, and the response will be similar. Okay, like this is the roots, alpha is different, omega is different, omega is the same here, and the response will be similar. I don't need to write the equations again and again now, right? For undertime response, alpha should be less than omega naught. That means 1 by 2 Rc should be less than 1 by root Lc. That's it. And what will be the response? Y of t. That would be e to the power minus alpha t C1 cos omega dt plus C2 sin omega dt, right? Here, what does that mean? 1 by 2 Rc should be equals to 1 by root Lc. And based on the initial condition, you can find C1 and C2, right? Initial condition, you can find C1 and C2. Because final condition, finally, y of t will be 0. all the parameters in parallel RLC and series RLC if there is no voltage source or current source. Let's just assume there is a circuit where is no source involved. What will be the final condition? Everything will be 0. Let's just assume a simple RC circuit. RC circuit. A capacitor is initially charged to V0 voltage. At steady state, what will happen? The capacitor current will go to 0, capacitor voltage will go to 0, resistance current will go to 0, resistor voltage will go to 0 because there is no source. So steady state will be 0 only. Whatever is happening in the circuit just because of this initial voltage, that's it. So if initial voltage is 0, sorry, if there is no source involved, there will be no final condition. Same in case of RL circuit. We have seen those examples, right? Same in case of RL circuit. If it is having initial current of I0, finally what will happen? Inductor current will go to 0, resistance current will go to 0, resistor voltage will go to 0, and inductor voltage will go to 0. Everything will go to 0. Same in RLC circuit. Whatever the initial condition is, but final condition, everything will go to 0. So in all the examples you will see, whatever the response we write, like for critically damped, what do we write? What do we write? C1 plus C2t e to the power minus alpha t. Initially you can have some value. If you put t equals to 0, initially you are having C1. But if you put t equals to infinity, y of t will be 0 only. At t equals to infinity, everything will go to 0. Okay. And what is in the case of overdamped? Alpha will be greater than omega naught. What does that mean? 1 by 2 RC should be greater than 1 by root LC. And what will be the response? C1 e to the power minus, not minus, directly you can write lambda 1t plus C2 e to the power lambda 2t. What is lambda 1 here? Lambda 1 is minus alpha plus root alpha square minus omega naught square. What is lambda 2? That is minus alpha square minus omega naught square. Here also if you put t equals to infinity, it will go to 0 because lambda is itself a negative value. Both are a negative value. Right? So this is the case. Okay. I don't need to write the equations again and again. Better we will solve some equations. But before that, we need to comfortable with the initial and final value. And these kind of questions are more asked in the exam. Okay. They will not ask these questions. If they are asking these questions, they will not expect you to find C1 and C2. They will rather want you to draw the graph. And how to draw the graph, that I have already told you. Right? What is the graph of overdamped? What is the graph of underdamped? And what is the graph of critically damped? So in critically damped, quickly stabilize with no oscillation. Overdamped, slowly stabilize with no oscillation. Underdamped, stabilize with oscillations. So that's how you can make the graph. And if you know the initial and final value, so based on initial and final value, you can draw the graph. Right? Let's just assume if they were asking the graph of VC in this one, they are asking the graph of VC in this one. Tell me, how will the graph look like? At steady state, VC will be 0. Initially, VC is V0. And based on the value of RLC, you just go to know that this is an underdamped system. Based on the value of RLC, you go to know that it is an underdamped system. And they are asking you the graph of VC. How will you draw? Initially, it is V0. Since I go to know it is an underdamped system, there will be some oscillations. And at steady state, it will go to 0. So this is how the graph will look like. Right? This will be the graph of VC. Are you getting my point? If they ask the graph, that is easy. Now, these kind of questions are very good when they ask the initial condition or the final condition. Here, everything is initial. I0 0 plus you find, V0 0 plus you find, or they are asking final condition. Okay. So, initial and final condition questions we will see in the next video. It will take time actually. Okay. Then what we will see? Then we will see sourced RLC circuit. What happens if there is a source? So, nothing different will happen. It will be the same as source free response, just a steady state value will come. Nothing else will come. Just as steady state value will come. Okay. Only the steady state value will come. Nothing will be different. Same alpha and omega for series RLC. Right? Everything will be the same. Then we will see for sourced parallel RLC. So everything will be same. Just this value will come. Okay. Then we will see 3 examples. First example, second example, and this is the third example. Okay. So these 3 examples we'll see, and with that we will be completing our RLC circuit analysis. Okay. And then after that we will see LC oscillators, and we will solve examples and assignments. Okay. And last topic would be AC transient, where we will see sinusoid response. So with that we will complete our transient analysis. So I guess it will take me around 5 hours more, not 5, I will say 6 to 7 hours of content is there. Okay. Okay, then let's meet in the next video. Thank you.